Hello and welcome to Distributed Systems and Blockchain in the News. My name is Thomas Bocek, and the first article we will look how much memory is used to run 1 million concurrent tasks. So I always say in my lectures that machines are fast, and this is a benchmark on how much memory such a runtime needs. And the author here compares different programming languages and runtimes. So he compares Rust, Go, Java. He has two versions, one the traditional way with threads and then the virtual threads. He compares C#, Node.js, Python, and Elixir. And then he shows numbers. There are two types of tasks in that setting. There are the native threads and the virtual threads. And with virtual threads, that means that you will have a pool of worker threads and the tasks will wait. And if a worker is free, then the task will be run on this worker thread. If you're using threads natively, then the operating system is responsible for that. So we see that with 10,000 tasks, how much memory an application is using, and he goes up until 1 million tasks. Let's go extreme. And here what we can observe is that these are runtimes only with virtual threads, so no native threads anymore. This is because, or most likely because, there's a limit on the number of threads per process. This you can actually change. So here you say how much threads you want to have at a maximum. This you can set. If you don't set it, then there will be a limit and you cannot run much more. Probably this is what happened here. So the measurements can improve for sure. And also in the last task, we see, for example, Go and C#. C# needs much less memory. Go needs more memory. So you might think, okay, Go is much worse at that. But there is actually more to it. Go pre-allocates 2 kilobytes per virtual thread, which is somewhere defined here. Yeah, we have it. And this is due to performance reasons. So I found another interesting article comparing C# to Go. This is a bit older, it's from 2019, but I think it still holds true, where one can see that C# uses less memory in overall. Here it's down at 1 gigabyte. Here we see it at 2 gigabytes for the Go routine. So 1 million times 2 kilobytes is for sure more than 2 gigabytes, so this makes sense. But if you also look at the time, is that it almost takes twice as long for C# than for Go. So this is clearly a trade-off for memory and speed. So pick one, and Go chose speed, needs more memory. C# is a bit slower but needs less memory. So the next article is about large language models. It's about off topic, but since we did a Power Week last week with Accelera, where we explored two use cases with large language model, it fits a bit. So the Power Week was this one here, where we explored in 100 hours GPT and large language models opportunities. And what I think it's interesting about this article, they have some very good points, namely the context windows, which is typically always too low. And the second point is that we have slow API calls. making multiple calls or chaining the calls, making it impractical. For example, we used GPT index to use as a means of providing more context, and if the framework, we used a long chain for that, starts to chain the calls, and one call is around 15 to 30 seconds, then if you start to chain the calls depending on what you need, then it gets terribly slow. So there you have to take care. And we use GPT 3.5 Turbo, which was the fastest, and GPT 4 is even slower. So we had to go with that one, which provides worse results than GPT 4, but it's much faster. And also, if you're using ChatGPT models, it depends when you do the query, we realized. So in the evening, starting at 8 o'clock and later, the queries were somehow much faster and delivered better results. And this shows that they have issues with many requests. And there's another funny story. It's about ChatGPT, where one person got legal advice from it, and ChatGPT came up with cases that even did not exist. He then used these non-existing cases in court. They were a bit confused. And we also observed a similar hallucination. And we used GPT index, and we had job profiles, and with those job profiles we had links in there. And when asking for a job profile, the model returned a valid answer providing a link which looked good, but the link was just made up and didn't even exist. And getting back to distributed systems, large language models is an example why you need distributed systems, why you need horizontal scaling. And you can run this on your own machine, for example, with Alpaca, with this one here. However, all the cores will be used. I used a pretty good machine, and it took a while to get the result. So here, if you have multiple users using your system as an API, you need horizontal scaling, as there are no machines with 10,000 cores yet. The last article is about Podman. It's this article here, and Podman is an alternative to Docker, which works similar. I also covered this previously in a video, and now there's even a nice GUI reaching version 1.0, and I have seen many students work with Docker Desktop, so if you want to switch to Podman, then there is Podman Desktop. I have not used it extensively, but maybe this could be a requirement for the next challenge task in 2024. And here a screenshot of Podman Desktop. Here we see it looks similar to Docker Desktop, where you can stop those containers and also start them. So this should look familiar.